Okay, 2.2 properties of matrix operations. Um, the properties of addition, matrix addition, are pretty simple. Addition is commutative. Remember that if you're going to add two matrices, they have to be the same size. Okay, so addition is commutative. Addition is also associative. So you can put those two guys together and you can switch orders and you can regroup however you want as long as it's addition. Remember that um, division, you don't ever want to, subtraction, you don't ever want to do that. You want to add a scalar multiple using a -1 as your scalar. Speaking of scalar multiples, if I have two numbers, these are scalars, times a vector, then I can group however I'd like, and you can also reorder however you like. I don't know why they put this in the book because it seems kind of obvious to me. The scalar multiple of 1 gives you your matrix back. If I have scalar multiple of the sum of two matrices, and excuse me if I accidentally say vector, these matrices are also actually can be considered vectors of many dimensions. If I have the sum of scalars times a matrix, then I can multiply each scalar. That should be, not that it matters, it's a D. I can manipulate it however I want. So matrix addition is pretty straightforward. There is also something called a zero matrix. The zero M by N matrix is just a matrix where every single element in the matrix is the number 0. And this should be like bold and big. That means if I add a 0 matrix, I get the matrix back. If I add the opposite, I get the 0 matrix. What else? If you have a scalar multiple of a matrix and the answer is the 0 matrix, this is an if, then either your scalar was 0 or your matrix was actually the 0 matrix to begin with. All of this is pretty straightforward stuff, right? Nothing that you haven't seen before. Let's talk about the identity matrix. All of this stuff was about the 0 matrix. The identity matrix we talked about a little bit before. It is a square matrix, always. So it just has one number because it'll be n by n. You can write n by n if you like. It is the matrix where each element along the diagonal, where I and j are the same number, is equal to, I made a mistake, the diagonal values are all 1s, and all of the elements, that's an I, are 0 when the I row doesn't equal the j column. So the diagonals are 1s, everything else is 0 in the identity matrix. Okay, so all of this stuff is pretty straightforward. So now we move on to some of the stuff that's not exactly as straightforward. First off, I'd like to remind you, when you have a system of linear equations, you either have a single unique solution, you have an infinite number of solutions, or you have no solution. And when we start using matrix methods, many different matrix methods to solve a system of equations, there's a quick and handy dandy little tool for you to see if there is no solution or an infinite number of solutions, and we'll get back to that later. All right, next concept, matrix multiplication. Ooh, multiplication. You need to practice it. It's not exactly easy, but you also need to understand the properties. All right, if I have three matrices being multiplied, I can group however I want. But notice that the order that in which I'm multiplying them did not change. What this means is I can choose to multiply the first two, get that answer, and then multiply the third. Or I can multiply the last two, get that answer, and then put the first one in front of that and multiply that. Whenever you're doing matrix multiplication, you need to write both matrices down and you need to put them in order before you do the multiplying. I didn't exactly do that in the last video, but I never switched them around unless I wrote it down to show you that it didn't equal. Speaking of not equaling, remember that matrix multiplication may be associative, but it is not commutative for all matrices. Every now and then you get two matrices that it doesn't matter which one comes first, but those are very special situations and examples, okay? So let's keep going. If I have a matrix that's multiplying the sum of two matrices, I can distribute as long as I don't change the order. If A is in the front, it's got to stay in the front. If I have A plus B multiplying C on the back end, then I'll have A times C plus B times C. But you never change the order when you're multiplying. If I have a scalar multiple of the product of two matrices, then I can either distribute the scalar through the A, then multiply the B, or I can say A times the scalar multiplied through the second guy. This was parentheses here. So it doesn't matter which one you multiply by the scalar, just remember that you cannot or you do not multiply both, all right? That would mean that you're multiplying by c squared. So do not do this. Also, and this is kind of important too, the book doesn't make a big deal out of it, but you need to know that there is no such thing as division. Sorry, wrong word. Division. No such thing as matrix division, okay? In other words, you cannot cancel. If I have A times B equals A times C, That does not mean that B equals C for all. On very rare occasions, it's the truth, but most of the time it is not. Okay, or many times it is not. You cannot just cancel out the A's. Got it? I'm serious. Please pay attention. Okay? There is no such thing as matrix division. We will learn a way to undo matrix multiplication using the inverse, but that comes later. Okay? So you can't just cancel the A's. You have to do something different to solve that matrix algebraic matrix equation. Okay? All right. Moving on to something new. The transpose. If I have a matrix defined as an IJ matrix, and then I find the transpose, and this is a superscript T to say A transpose, then this is J first and then I. All I did was you switch. I can't spell switch. Starting over here. Sorry about that. I'm going to switch the rows and the columns. Columns. Okay? So if I have 1, 2, 3, 4, 5, 6 as my A, then A transpose is going to be 1, 2, 3, 4, 5, 6. So I went from being 2 rows by 3 columns, and now I have 3 rows by 2 columns, and I transposed. In other words, what was a row is now a column. Row 1 is column 1. Row 2 is column 2. Column 1 is row 1. Column 2 is row 2. And column 3 is row 3. Got it? So transposing is just flipping it. You can transpose any size matrix, and transposes have special properties, and you can use transposes for things, and we'll get into that later on. Properties of transposes: if I have A transpose and I transpose it again, what does that mean? It means I flip the rows and the columns, and then I flip the rows and the columns again, and I'm going to end up right back where I started from. If I have the sum of 2 matrices and I transpose that sum, I'm actually summing the transposes of the individual matrices. If I have a scalar multiple of a matrix and then I transpose that, I have the scalar multiple of the transpose of the matrix. All of these should seem pretty straightforward once you get the hang of how matrices work, until you get to this one right here. If I have the multiple or the product of 2 matrices and I transpose that, then I don't get A transpose times B transpose. I get them backwards. Okay, that's the one that's a little bit hard to catch on to, but you'll see it in some examples, which we will show right now. Okay, I'm assuming that all of those properties that we just went over with multiplication and addition and scalar multiplication, associative, commutative, all of that stuff is really straightforward, and I assume that when you're doing your homework, you can figure that stuff out for yourself. but I want to give an example now of that final property. So I'm going to let A be 1, 2, 3 by 0, -3, 4, and let B be, let's see, it's so hard to be random, -1, 3, 2, and a -4, 1, 1. Then A times B. Can I multiply A times B? You have to pay attention to the sizes, right? A has 3 columns. B has, sorry, A has, no, I cannot multiply those. Ah, good lesson, right? Yes, I can. Never mind. Darn it. Good lesson. I have 3 elements in a row and 3 elements in a column. So I'm going to multiply, 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 and add those guys together. So I just really confused myself there for a second. So because this guy was 2 rows by 3 columns, and this is 3 columns by 2 rows, my answer is going to be a 2 by 2. The inner numbers have to match to be able to multiply, and your answer is the size of the outer numbers. Okay, so now let's find this answer. So I'm going to multiply across and down and add the answers. So I get -1 plus 6 is 5 plus 6 is 11. Ooh, big number. Now, row 1, column 2 gives me row 1, column 2. So I multiply the 1 times -4, which gives me -4. Then I'm going to get a +2, which is -2. +3 is a 1. Second row, first column will give me second row, first column. So when I multiply here, 0 times -1, that's a 0. Then I get a -9 plus an 8, I get a -1. Next, row 2, column 2 gives me 0, -3, +4, and I get a +1. So that's A times B. AB transposed will be row 1, column 1 stays the same, but the top row becomes the first column here in the transpose. So that 1 moves down here. Row 2 in the original becomes column 2 in the transpose. And what you see is that we just flipped it on the diagonal. Okay, now A transpose, we're checking here, is going to be 1, 2, 3, 0, -3, 4, because the rows became columns and the columns became rows. B transpose is now going to be 2 rows and 3 columns, and the rows -1, -4 became a column. Row 2 is column 2, row 3 is column 3. Now let's find A transpose, B transpose. This is the kind of thing that you're going to be doing in your homework. I have 1, 0, 2 times -3, 3, sorry, not times. There we go. There's my A. Here's my B transposes. Just writing them beside each other so I can multiply them. This started as a 3 by 2. This is a 2 by 3. We're going to end up with a 3 by 3 matrix. Okay, let's do this thing. And then I'm going to erase it because I want to show something else and I'm running out of room. So I multiply the row times the column, so I get a -1 and a 0, which is -1. Row 1, column 2 gives me 3 and a 0, which gives me a 3. Row 1, column 3 gives me 2 and a 0. Now row 2 times each of those columns. I'm going to get -2, +12. Column 2, I get 6 minus 3. Column 3, I get 4 minus 3. Did you follow that? I took this row and multiplied each column. So I had 2 times -1, negative times a negative is a positive 12, -2 plus 12 is +10. Then I did this column, so it was 6 minus 3 was 3. And then this row, this column, gave me 4 minus 3, which was 1. Do this third row now, times each column. I get -3 minus 16 is negative ugly number, -19. Column 2, 3 times 3 is 9, 4 times 1 is 4, 9 and 4 is 13. I hate minus signs. Last one, 3 times 2 is 6, plus 4 gives me a 10. This does not equal AB transpose. So we just proved that you can't do that. AB transpose was this little thingy here, right? So remember in that property, when we took the transpose of the product, we ended up with the product of the transpose, but in reverse order. So what I need to do is find B transpose times A transpose and see if that equals. So let me, whoops, I thought I could do all of it. Here we go. All right, let's do B transpose times A transpose and see if we get what we're looking for. B transpose was 2 rows and 3 columns. A transpose was 2 by 3. So my answer when I multiply these guys, this was 2 rows, 3 columns. This is 3 rows, 2 columns. My answer will be a 2 by 2, which is what I'm looking for, right? Where I found AB transpose, excuse me. All right, taking my row times my column, I'm going to get -1 plus 6 is 5 plus 6 is 11. So far, so good. Row 1, column 2, I get a 0, -9, +8 gives me a 1. Row 2, column 1 gives me -4 plus 2 plus 3 gives me +1. And then the last guy, wait a second, let me go back because this guy has the wrong sign. Let me double check myself. You should do the same. We did row 1, column 2 to get row 1, column 2. So row 1, column 2 gives me minus 0, right? There's a -9 and a +8, and sure enough, I missed a minus sign. Good thing I checked myself. Now moving on, row 2, column 2 gives me 0, minus 3 plus 4 gives me plus 1, and you see that that is equivalent to A times B transposed, okay? So that's the kind of stuff you're going to be doing in your homework. You're going to be finding sums, you're going to show that they're commutative, you're going to be finding products and showing that products are not commutative, things like that. So have fun. Remember, your homework is 1 through 47 odd, and we are in 2.2.